Hello everybody, this is Mike. Welcome to this Fusion validation model. This is the ninth one that I'm doing in this series. And today we're going to take a look at the model that we have here, which is a thick-walled spherical vessel, or at least a section of it. So we're going to take advantage of symmetry, and that will help reduce the size of the model that we have to work with, as well as make the analysis itself a little bit faster to run. So let's take a look at the description here. It does come from Rourke and Young. From the 5th edition, it's from 1975, it's page 506, table 32, case 2A. And again, a thick-walled spherical vessel. We are going to give it internal pressure, and we're going to analyze it for radial stress and deflection. So the outside radius is 10, the inner radius is 7, pretty simple geometry, and the internal pressure that we're going to use is 10 KSI or 10,000 PSI. The material properties that are given to us are a Poisson's ratio of 0.3 and a Young's modulus of 30E6 PSI. We'll talk about that in a little bit once we get into the simulation itself. Again, we are going to use 1/8 symmetry, and what we expect to find is a max deflection of 0.002796 inches and then a max stress tensor of 12,831. So once we get our results, we can plug those values in and figure out what our percent difference is. So just real quick, let me show the sketch here. I just started out with two circles. You can see the diameters on them, 14-inch diameter and a 20-inch diameter because of the 7-inch radius we want and the 10-inch outer radius. From there, I just drew two lines so that I could quarter it, and then I used the trim tool and cut off the sections of it that I don't want. And then I just did a 90-degree revolve around the y-axis. So you can see that I sketched mine in the XY plane. So presuming you are going to maybe create this on your own, if you create it in some other plane, when you are trying to follow along with the constraints, just make sure that you adjust your constraints accordingly depending on the particular orientation, what plane that surface would lay in. So let's go ahead and move in the simulation. From the design pull down menu, now that we have the model drawn, we can go into simulation. As we go in, we're going to select the static stress model. So I'm going to go ahead and say create study. And here inside of the simulation workspace, one of the first things that I do, generally working in a left to right progression or top to bottom in the browser, one of the first things that I do is assign the materials. And given that this one is a 0.3 Poisson's ratio and a 30E6 modulus of elasticity, those of you who have seen some of my videos before know that I created my own library, and I put those properties in. So if I choose my own library, Mike's Materials, from the pull down menu, you can see there's an A36. That's the material I based it on, steel A36, but then I made sure that it had a modulus of elasticity of 30E6. So there are other videos out there if you need to know how to create your own library. Likewise, I think the documentation is really good for it. In this case, what I'm going to do is just use something that is available to everybody in the library. I did a little bit of looking around in the library, and if I choose the Fusion 360 material library, so that way I shouldn't see my custom materials, and we just scroll on down. There's a material here under the stainless steel. It's just referred to as steel. If I click properties on that, you can see the density is 0.2836. Young's modulus is pretty close. It's 30.46 e to the 6 instead of the 30 e6 we were looking for. So that will have a little bit of impact on our results. Poisson's ratio is 0.3. So for this particular walkthrough one, I'm just going to use the steel material out of the library. But again, if you are going to follow along with the videos and do a lot of these yourself, a lot of the material inputs throughout the works presume a Poisson's ratio of 0.3 and a modulus of 30e6, so it might be worth creating your own library and at least adding that material in. Again, I'm just going to use the steel that's in that library, so I'll say OK to that. And if I expand study materials, I should see that that material is now assigned. Next thing is the constraints, and the constraints are the kind of one of the big things with this model, right? Because it's a sphere, and we obviously have 1/8 of it here. So I do need to do my symmetry constraints, and the symmetry constraints are stopping the translation of whatever is vector is perpendicular to that face that we've cut through. So this face here, if I rotate this model around, looking at my mini axis here, right? Y is vertical, Z is kind of off to the right, and then X would be kind of into the screen here. What we want to do is constrain the translation perpendicular to the plane of that face. So in this case, I want to constrain the UZ direction, and we'll say OK. So this face here, this is the one that is in the plane YZ, so X would be the perpendicular, so I want an X constraint there. So again, constraints, and we'll constrain the X direction and say OK. So there's my Z constraint, there's my X constraint. You can see that Y currently is vertical, so that means the bottom face, my bottom symmetry face, that's the one that's going to get the Y constraint. So again, constraints, uncheck UX and UZ, and we'll assign the UY to that one. All right, so we have the material, we have the constraints. Next that we need would be the load, and when I go to loads, by default it's coming up with force. We do want a pressure in this particular example, so selecting pressure or changing the type to pressure, and you can see we have a number of different types of loads if you're new to the program. Pressure, and I'm going to select that face that would be the inside of this vessel, and it's 10,000 psi. Okay. If you are using different units, by the way, if you installed your Fusion with some other unit system or in the options you have changed units, as you apply something to the model, you can change the units right there if you need to toggle them to make them PSI for this particular example, for instance. Just be aware that you can do that. Let's go ahead and say OK. We don't have to worry about contacts. That's just for assemblies. Normally, you don't have to mesh the geometry. As you go ahead and kick off the analysis with the solve button, it will generate the mesh. But in this case, I'm going to go ahead and tell the program, let me just go ahead and hit generate mesh, what I want the mesh size to be. I think the default mesh is going to be a little bit coarse here. You can see that it's got 3 elements through the thickness. Given what we're going for in this particular model, I want that to be a little bit finer. So I'm going to right click again on mesh and say mesh settings. And in the mesh settings here, what I'm going to do is choose an absolute size, and then I can type in the mesh size that I want. So given the 10-inch outer radius and 7-inch inner radius, that's 3 inches, right? So if I go with a 0.5 and say OK, and then generate that mesh, that should give me a good many more elements through the thickness on this model, right? So there we can see our new mesh. That looks good. I think that should do just fine. And at that point, I think we are ready to execute the analysis. So let's go ahead and choose to solve it. Again, with Fusion being a cloud product, you can choose whether to solve it on the cloud or whether to solve it locally. We're going to say solve it locally, save ourselves a couple cloud credits. And it's not that big of a problem, so it should solve pretty quickly on your computer. Expand the details here. You can get a little bit of information about what phase it's in. All right, so here we are in the results. Automatically moves you to the results once the results have been computed. In our case, it's defaulting to the safety factor. That's not one of the things that we are going to validate or check in this model. In this model, we want to take a look at displacement. That's a known value for us. And we can see that our max displacement is 0.002767. So if we bring over our spreadsheet and we enter in that value 0.002767 in comparison to the theoretical hand calculated result, we get a 1% difference. So I think that is a really good result there. And then the other thing that we want to take a look at is the stress tensor. And in this case, what we can do is take a look at the tensor in the y direction. So we're going to choose stress, and then it's going to default to von Mises by default. So let's take a look at normal y, and that shows us a result of 13,070. So if we plug that in, 13,070, and we hit enter, so there's our percent difference in the stress value. We're less than 2% different. So I think we have really good agreement there. So hopefully that is a useful example for you, and thanks for watching. Have a great day.